saying, I'm very happy to introduce Brendan. We go way back to grad school, and then he was a postdoc here for a couple of years. I know now he's doing great things now, and he's an assistant professor at Brown now, and I know he's doing great things. And I'm very happy to looking forward to listen to this talk, which, as the title says, is about proximal Galerkin, which is a method for variational problems with inequality constraints. Some of you might be familiar already, some of you not. So please, Brendan, take it away.
Thank you, Socrates. Thanks to all the organizers for inviting me to speak here. Seminar series. It's been a lot of great speakers over the years. I feel like I'm a very good company. So so I want to tell you basically about main line of work that I started. Maybe the initial ideas were actually founded while I was at the lab, but I really started exploring them once in new ways once I came here to Brown. So I'd like to share what we've done over the last few years. So the talk will proceed following roughly the agenda that you see here. I'm going to spend some time trying to motivate the class of problems that this method is meant to tackle, and why I think inequality constraints are some of the most interesting areas of research in scientific computing right now. There's lots of open problems, and they arise everywhere. Then I'm going to talk a little bit about the technical approach that leads to the method, the proximal Galerkin method. So then in order to do that, I need to introduce some ideas from convex analysis and brief ideas from differential geometry and put those together in a way that's suitable for applying the finite element method, and that gives us the proximal Galerkin. Then I'm going to show some things you can prove about the method, but really this talk is about the applications. So throughout, I'm going to interleave many different applications where this framework can be applied, some of which are listed here, but many more you'll just have to wait and see as they come. So I always like to start at what I really think of as the bread and butter of scientific computing. These are the problems that I think the flagship strategies deal with very well. This is what we do in scientific computing all the time, and I think we do it very well. So what is it? Enforcing linear equality constraints, or sometimes more general, just equality constraints. So where do these appear? We might have a physical model, like an electromagnetism. We want to make sure, because in the actual model, there are no magnetic monopoles. We would like to make sure that there's no magnetic monopoles. When we discretize, and that roughly speaking corresponds to enforcing this differential equality constraint. If we're evolving a molecular system, a closed molecular system, there's another physical property we'll probably want to enforce. That's the energy remains constant in time. We can also do this to great accuracy in scientific computing. Another class of problems that has strong lab relevance is material transport. Now, you can debate with me whether we do this well enough or not, but I think we do it very well, at least in the case where we move the mesh. We actually treat this equation in Lagrangian frames. It's actually when we remap and reset the discretization where things get kind of tricky, and that's actually also where inequality constraints arise again. But in each of these different problems or classes of problems, and there are many more, we're enforcing some sort of equality condition or equality constraint. And then from the very highest level, what are we doing? A lot of these constraints, not all of them, uh, we have some ambient function space, and we need to lie on some subspace of that function space. So the Galerkin method is perfectly well suited for doing this because it's a approximation scheme based on subspaces. And we can very easily navigate those subspaces which define the constraint, both at the continuous and discrete level. And that's sort of how the final method is really, this is what it's really designed for. There are other problems also where we maybe lie on a closed manifold, and there are other ways to make sure that we don't leave the manifold and navigate it. At the end of the day, these are the closed class methods. These are what we often teach to students in classes, and they lead to the most systematic, robust solutions to a wide variety of different problems all across scientific computing. This is the bread and butter. But not every problem in scientific computing obviously falls into this category of equality constraints. There are also inequality constraints, and they are at least as important as the previous category. So where do these arise? Probability distributions or density functions to be non-negative. Material densities likewise also have to be non-negative. There might be maximum principles that come from the model, and we want those to be enforced at the discrete level. Optimal design, we have box constraints, multi-place flows, other constraints, inequality constraints, and we want to preserve those. But it gets much more complicated than that. There can also be non-convex constraints produced in contact. We may want a body may not penetrate another body. That can be seen as an inequality constraint, but we want the body not to penetrate itself or to interpenetrate when it's deformed. These are also inequality constraints of a different nature, but also as important. Or there might be an arrow of time that we want the simulation to respect. For instance, we're simulating some damage to a material through fracture, plasticity, or otherwise. We want to make sure that we know that the original model doesn't have any mechanism to spontaneously heal the material. We want to make sure that that's also enforced at a discrete level. So these are inequality constraints on time derivatives you can think of. And there are many more than these three examples, but at the very highest level, what distinguishes it from the equality constraint setting is that we're not navigating a closed subspace of some function space. Maybe in the simplest setting, we're navigating some convex subset of that space of functions, maybe a polytope or otherwise, but it has a boundary, and that's often the issue. And it can get more complex if you have constraints which are non-convex and you're navigating some manifold with boundary. And what we need is a way to navigate these manifolds with boundaries that's somehow respected by the discretization. And if we don't somehow respect this boundary in the discretization, we fall into another class of solution strategies. I like to think of these as sort of the discretize and repair side of scientific computing, where you make a discretization, you don't restrict these constraints, and then you have to adjust it or reset it or do something else. Now, these problems are so important, obviously they have to be solved, and people have been looking at them for decades. It's not like they've just been there waiting for somebody. People have been studying them, they've been developing methods. A lot of these methods are lowest order. The ones that are higher order are best specialized to different fields. The things that people do in fluid mechanics are often very different than the techniques developed in solid mechanics or in optimization areas. And there are no unifying principles, no unified framework to deal with all these different types of constraints. And that's what this talk is about, is an attempt to put together a unified framework where we can systematically handle constraints of all of these different types across scientific computing. Okay, so how do we do this? It's very ambitious. We're partially there. I'll show you what we've done over the last few years and where we aim to go. But I first have to give you an idea of what's the foundational concepts that our approach is based on. And the way I like to start is sort of this simple setting. How can I give you kind of the simplest geometric example of what inequality constraints look like? Look at the upper half plane of R2. And we need some way to navigate upper half plane. And the sort of simplest thing one could think of is just transform to new coordinates. So somehow we know how to navigate R2 perfectly well. So if we transform this upper half plane, we can map it into R2, and then we can discretize or whatever we want over here, and we'd have to maybe map back. Now these transformations, ideas of changes of coordinates, it's not new. And they've arisen in different top texts, but there's different questions you need to answer if you want to go this route. First of all, how do you generalize this to more complicated sets? And not everything is just a unilateral box constraint. And how do you make this compatible with the functional analysis and the study of these PDEs or variational inequalities that actually have these inequality constraints, because this transformation is singular, and that presents a barrier once you discretize as well. So there's a way to get around this singularity and treat general constraints and all of these things. And the first step along that path is to introduce the concept of a Legendre function. Okay, so what is a Legendre function? This is actually an idea that goes back to the 1960s. Terry Rockefeller, who's still with us to this day, actually, he was visiting us at Brown last week. He's the kind of the godfather of convex analysis and built most of the field on his own. So the concept of the Legendre function, he was looking at what are the classes of functions that the Legendre transform is well defined on. And it turns out it's a class of functions, they're not quite barrier functions, that have a certain singularity at the boundary of a convex set. So the domain of the function is the essential domain of a function. These are extended real-value functions, so maps from Rm to R, or including infinity. The essential domain of all the points in Rm that are mapped to finite values. We need a differentiable function on the interior of the domain. It needs to be strictly convex in the interior of the domain. And it has this condition, which says that the gradient of the function blows up as you approach the boundary. Not the function itself necessarily, so don't think of just a logarithmic barrier. Think of something like the Shannon entropy that's well defined everywhere over its domain, but blows up in its gradient on the boundary. Okay, and it turns out that this function can be used to encode pretty much the complete differential geometry or Riemannian geometry of a convex set. All right. I'll show you this one step at a time. So we take a set C, convex set C, and our task is to find a Legendre functions whose essential domain is equal to C. Now there's a theorem from Rockefeller in 1967 that tells you that a Legendre function's gradient, okay, is a bijection, a smooth bijection, a diffeomorphism between the interior of that domain R, so the interior of your convex set C, to the interior of the domain of the conjugate function. So this is conjugate function given to by the Fenchel-Legendre or Fenchel-Rockefeller transform here. The transform is basically encoding all the information in the convex hull of your function's epigraph, rewriting the function in terms of the function of those supporting hyperplane. All right, I'll give you a bunch of examples here because this is the most abstract part of the talk. But this fundamental theorem tells you that you have this isomorphism on the interior of your convex set C, given a specific function like the Legendre function. And there's another fact, also proved by Rockefeller, that the domain of the conjugate function is all of Rm, if and only if you have this growth condition. So this is saying that your function grows faster than any linear function as you move away from the origin. Okay, this is called superlinearity or what convexity, supercoercivity. There's many different names for the same concept. Optimizers have it settled on what they really want to call it, but it's a well-known common condition. And if you have this, a de Legendre function with this condition, then what this fact and this theorem tells you is that the gradient of the conjugate function is a map from Rm to the interior of your C. So this is your transformation. You define your Legendre function, and you get your coordinate transformation from it. So examples are required now. This transformation I showed you a few slides back from the half plane. Okay, this logarithmic transformation. Well, this should be the gradient of something. Turns out it's the gradient of this Legendre function. So it's quadratic in its first coordinate, and it looks like the Shannon entropy in the second coordinate. But obviously not every constraint looks like this. But if we, well, I'll show you some other examples in a second. Let me just review the parts of the theorem. So this transformation, it turns out it will always be singular, because actually that's the part of the definition of the Legendre function. Its gradient needs to blow up as you approach the boundary of your convex set. But the beautiful thing about this class of functions is that the inverse transformation is always smooth. So for instance, this one is inverse, looks like x times the exponential of y. This is infinitely differentiable. Beautiful transformation moving back. And by convex duality, Machiavelli's theorem, the inverse of the gradient is the gradient of the conjugate function. Okay? So now this, because the inverse is always smooth, it actually directs us in deriving discretizations. It means we should discretize here where we know how to do it well. And if we use the inverse transformation, we will map back into our feasible set. And that's exactly what Legendre functions allow us to do. Okay, it gives us a beautiful systematic way of designing coordinate transformations from a given convex set to Rm and then back, and we can use that in constructing discretizations. And I'll show you how to do that in 10 or 15 slides. But now some more examples. So if we have box constraints, so upper and lower bound constraints, you can use this transformation, this logistic transformation. It's also given to you by the gradient of a Legendre function. Here you have quadratic in x, and this in y, this is called the Fermi-Dirac entropy. If you have ball, some sort of unit ball constraints, there's an inverse radial coordinate transformation. It's also the gradient of a Legendre function. This one here, which is sometimes called the Hellinger entropy. Each map is singular. Each inverse is infinitely smooth. And I'll give you many more examples later. But we need a little bit more than just a transformation. It turns out the Legendre function also gives us a geometry, a Riemannian structure to the convex set. And we access that structure by actually looking at the Hessian of the function. So we have a Legendre function, gradient is a transformation. We can treat the interior of C as a Riemannian manifold with a metric given by the Hessian of R. Now remember, one of the properties of R was that it's strictly convex. So the Hessian, okay, this is always a positive definite matrix at every point. Then we can, once we have the metric defined, we can define geodesics, concept of straight lines on our manifold. And it turns out that under this metric, we have curved lines. That's how we would navigate, move from A to B in our feasible set. But under the transformation, they turn into straight lines over here. And this means that we design an algorithm where we just want to define an additive update rule like gradient descent. It's very convenient to do it over here and then transform back. We can also define a gradient flow on our manifold. So we would choose, instead of the Euclidean gradient on our feasible set, we can choose the Riemannian gradient that comes from, that's informed by the metric. So in Riemannian geometry, instead of using the Euclidean gradient, you precondition it with the inverse of your Hessian, which turns out to also be the Hessian of the conjugate function, but as a chain rule that I'll spare you. So here you have a gradient flow, and this is pretty much a direct path towards designing an optimization algorithm on on your feasible set. You define F, and it's restricted to C. You want to find the minimum. You can follow the Riemannian gradient towards that minimum. Okay, and how do we usually discretize gradient flows? Well, we use steepest descent, or otherwise known as explicit Euler. If it's an Euclidean gradient flow, we have this equation here. It's well-known explicit Euler formula. It's just the rewriting of steepest descent. Optimizers also know that you can just cover this update rule by just minimizing this quadratic subproblem, where you linearize your objective function, penalize the distance from your previous point using the norm squared, and the local minimizer, or the minimizer, will be your next point in your descent method. Now you can ask an obvious question if you look at this linearized subproblem: well, do we get a more accurate update if we use the full objective function? Yes, you probably do, is the answer. And the subproblem would look something like this, and optimizers call this the proximal subproblem. This is actually where proximal and proximal Galerkin comes from. If you solve this subproblem, and there's no constraints, it turns out you get implicit Euler. Okay, we would say that this problem is maybe more accurate because it's the implicit Euler scheme is stable for any choice of alpha. Otherwise, you can do an updates rule where the update point, or the point we're computing your gradient, is defined implicitly in terms of where you're going to end up. So this is uniform. You can think of it in two different ways. This is a step size rule where you can use any alpha you want, or it's an ODE integrator that's uniformly stable, or in alpha. Okay, we want to use this idea for Riemannian gradient descent. Now our gradient looks a little bit different. We have this Hessian term here, and now there's this little trick that we can use. It's called the chain rule. We take this equation, we multiply both sides by the Hessian of R, and we would get this term on the left-hand side of our ODE, and then just the gradient of F on the right-hand side. But by the chain rule, we know that this term here on the left-hand side is just the derivative of the gradient of R at U. This right-hand side we could discretize with implicit Euler, and we get this update rule here. Okay, now instead of looking at a divided difference in terms of just U, we're looking at the divided difference in terms of this transformed U, where we have the transformation coming, the gradient of the Legendre function appearing. Now this update rule is also well known to optimization community. This can be rewritten just by multiplying through by alpha, as you can call it the Bregman proximal point iteration, which is equivalent to minimizing a different proximal subproblem, where instead of penalizing with the squared Euclidean norm of the difference between U and UK, you penalize with something called a so-called Bregman divergence. Okay, what's a Bregman divergence? Well, a Bregman divergence is basically a generalization of the squared norm, but it's generated by a Legendre function here. It's looking at the linearization error in your first order Taylor expansion of your Legendre function at a point. And if your Legendre function is quadratic, then you actually get back the squared Euclidean distance in the proximal point method. So let's say that R is the Shannon entropy, and we want to look at compute the distance between U and a different point. And if we do so, we could vary U, and we would get and we get when we vary U, we get a different tangent plane, and we can vary the point we want to measure the distance from, and the Bregman divergence is the distance away from the tangent plane. So if we now basically rotate our function by subtracting off this linearization, we see what the Bregman divergence is. It's a everywhere positive or non-negative function. It's non-symmetric, and it's this generalized squared distance between U and V. Right? And as you vary V, you end up seeing that at the boundary of the domain, the tangent plane is vertical, meaning that the distance between V and U ends up becoming infinity. And the takeaway message is because the distance sort of grows, it's penalized non-symmetrically between these two different points. Every iterate of your method stays in the interior. You generate an interior sequence of points that converge to your minimum, as you would expect. You're evolving you're running a gradient flow. If this is the time discretized version, but every point of that time discretized version evolves within the feasible set. Every iterate takes you to a lower function value. So that's what this video is showing. You take F, you penalize F with your Bregman divergence, you get a different subproblem and when you find the minimum, you always find a minimum at a lower point than what you started with. Okay, so that's Bregman proximal point in a nutshell, and the rest of the talk is about how to use this for mechanics. We have everything we need in our Legendre function, the coordinate transformation, as well as the geodesics and our Hessian, and our gradient flow scheme. So what problems do we often find in mechanics? They look something like this. This is sort of the hello world of inequality constraints. You're minimizing the Dirichlet energy. Instead of just fixing the points on the boundary, which would give you Poisson's equation, you have fix the points on the boundary. So you're minimizing an H1, but you also have a constraint on the function lying above some obstacle, which is defined through the graph of this function phi. So the equilibrium point of this, or the minimizer of this energy ends up giving the equilibrium position of a thin membrane lying up, clamped on the ends and lying above this obstacle. But not every problem looks like this. If you have real contact, then the contact is only happening on the boundary. You minimize some other objective function, always more complicated, and some product of H1, whatever boundary conditions you want to consider, and then you want to make sure that as long as it gets more complicated when you incorporate friction, but at the very least, there's no penetration constraints. So the normal component of your displacement variable has to stay above something called the gap function. Now, finite element methods for obstacle problems and contact, many other models have been well studied, but something that's been very hard for finite element people to do for a long time is to solve the Iconal equation. So this is nonlinear PD here. There's some famous schemes of finite difference methods to do this. And I know people that have to solve this equation that sometimes actually take their finite element code, export it to a finite difference code, solve the Iconal equation, and then interpolate back. There's this whole awkward pipeline that they have to follow, including some friends of mine. It turns out that Iconal equation, the viscosity solution of an Iconal equation can also be written in terms of an optimization problem. Here, what you're doing is you're trying to find the maximum mass density field in a feasible set with an inequality constraint on the gradient of U. And it turns out the maximizer, the optimum at this point, ends up giving you a point in space where this constraint is active almost everywhere. So this becomes an equality. In all of these examples and many others, you have feasible sets that look like this. You're looking at set of functions in some Banach space V, and then you have an operator. I'll assume for this talk that it's linear. So in the case of the obstacle problem, B was the identity. In Signorini, it was the normal trace. In iconal equation, it was the gradient. So some operator applied to this function and evaluated at a given point has to be in some convex set. And then this constraint needs to be satisfied at almost every point in some subset of the closure of omega. And if your feasible set is of this type, we have a table of Legendre functions you could possibly use that encode the geometry of C. Feasible sets of this type are not just appearing in those three examples. They appear in topology optimization, fracture, plasticity, and other nonlinear PDEs than iconal, including the Monge-Ampere equation. I'll assume we always have an energy principle, so we're minimizing some objective function J over this set K. And what I'm going to use is this somewhat, I would say, we've been looking at this for a long time, so I'm tempted to say straightforward, though I know it's not. It's really much the only way you could apply Bregman proximal point to a feasible set of this type. You take your objective function, you penalize with the Bregman divergence, but now it's not a Bregman divergence necessarily on the argument, it's on this operator applied to the argument, which is called the observation map. So in obstacle problems, this operator is the identity, the gradient, so on. And you minimize this regularized problem at each step. And because the Bregman divergence is giving you an interior point in your feasible set, when you write out the Euler-Lagrange equations, you get a nonlinear PDE. Okay. Now, because this is very abstract, the PDE has all of these symbols in it, but I'll give you some examples in a minute. And in general, it looks like this. And you solve this PDE at every iteration. Now, the drawback of this PDE is that the gradient of R is singular because it's the gradient of a Legendre function. So for instance, it could be like a logarithm. So the way we get around that is pretty much the oldest trick in the book. We introduce a new variable for the term we don't like. We call it psi, the latent variable. And the first thing we do is we rewrite our equation as a system of equations. The first one is taken the singularity out. And the second one, we've kept it, but we can use a trick because we know that there's an inverse to this gradient that's nice and smooth. So if we apply the inverse to the second equation, then we get a smooth equation back. In fact, both equations are nice and smooth. And this is the thing we discretize. So you start with a variational problem with inequality constraints. You regularize it, you get a sequence of nonlinear PDEs. Use this is called Fenchel-Rockefeller duality to rewrite the PDE in the saddle point form. And then you discretize that PDE in saddle point form. Because it's all done in a loop with these are proximal subproblems where the right-hand side depends on the previous solution. And the Galerkin comes from the fact that we choose Galerkin subspaces of our function spaces where this problem is posed. And because the inequality constraints are imposed weakly in the second equation, we don't have to worry about discretizing the feasible set directly. We discretize it somewhat indirectly, meaning we can choose any subspace, compatible subspaces that we want, V and W. This means we can go arbitrarily high order, any basis function you like. So if we apply this to the obstacle problem, for instance, okay, then the weak formulation, I'm going to play substitution here. We have, I'm going to first look at derivative of J. Well, this is the Dirichlet energy. Oh, sorry, I forgot the order of my own slides. B is the identities, so let's simplify those terms. Then we look at J, we simplify that. We're taking the Frechet derivative of the Dirichlet energy, and then the final thing we have to decide what to do about is the choice of the Legendre function. And I advocate for using the Shannon entropy, but there are other choices that you can also consider. And if you use the Shannon entropy, you end up getting exponential of this variable psi here. And that's your system of equations that you can discretize. Now, because of time, well, let me say one more thing before I move on. When you discretize this, you get two variables. You get one UH that's in a standard finite element space piecewise polynomial, but you get a second variable, and this is non-standard. And that just comes from looking at this part of the equation. Phi plus the exponential of psi is another approximation to U. And this one will always be bound preserving, no matter how high order you go. The method itself will converge. You don't need to send any parameter infinity, unlike penalty or interior point methods. You always get a bound preserving approximation. I'll skip this. This is a comparison to interior point, Lagrangian, and other schemes, and move on to other examples that you can consider. In the end, it turns out our method is mesh independent. You get the same number of iterations, unlike some others. And the number of iterations is very similar to interior point. So for Signorini, you get a saddle point system, same original form, but the operator B is different. So it's the normal trace. So we have to substitute that for first. I won't deal with what the energy function is here. This could be very complicated. But the Legendre function could still be the Shannon entropy because the constraint is unilateral. So using the exact same Legendre function as for the obstacle problem, you get a system of equations that looks like this. Now you have a variable u that's defined over the domain and a second variable that's only defined on the compact part of the boundary, but otherwise it's very similar to the obstacle problem. And then finally, for the iconal equation, system equations, now simplifies setting b equal to the gradient. The derivative of the objective function, the objective function is linear, actually, so that we have a very simple looking derivative. It's actually something you can move to the right-hand side of this system. But the Legendre function is very different than the previous two examples because the constraint is different. We're trying to make sure that the gradient stays inside the unit ball. So you could use the Hellinger entropy for this case, but there are other choices. If you use the Hellinger entropy, then you get a system of equations that looks like this at each iteration. Other things you need to consider, what solver do you use for these nonlinear subproblems? The first choice is Newton, but there are other choices you could consider. And then once you choose your subproblem solver, you're going to get linearized subproblems, and you'll have to decide how to solve those, design preconditioners for those. A lot of that is still open area of research. We have strategies that worked depending on the Galerkin discretization you've chosen. But a lot of the cases, because of the symmetries, you don't have to just rely on GMRes. You could use MinRes. But I won't dive into that too much. We've implemented Proximal Galerkin in several different finite element codes: Phoenix, FireDrag, ngSolve, but most prominently in FEM, where there's actually 3 examples that you can play with if you'd like, including one for the diagonal equation. Now, I'm in a math department, so I'm obligated to prove something, and I'd like to prove that this very interesting property. This is well known at the continuous level, that every iteration of Bregman proximal point is going to decrease the energy. But there's something very special about the Galerkin approximations of these subproblems that guarantee that the energy continues to decrease. There's no H-dependent term in this decrease. It will always decrease every compatible Galerkin approximation. The proof is actually just a few lines showing that somehow the Galerkin approximation is preserving the structure of the original algorithm. So the first step is just the standard subgradient inequality, and every other step just involves using the definitions of the proximal Galerkin subproblems with different choices of test functions. So this term here, J prime of UK, looks a lot like this term here in the first line. We could set VH to be anything we want, and the convenient thing to do is to set it to be this difference here. And if you do that, then you can rewrite the first line as follows. And it turns into something that looks a little bit like the second line. And if you set WH to be this difference of these latent variables, then you can rewrite the second equation in this form. Here, okay. Now this is a term that we in optimization really like to see, because this term for any convex function is always non-negative. It's basically telling us that the gradient of our convex function is monotonic, and this is and because this is always positive or always non-negative, we know that the objective value always decreases. Now you can prove a lot more than that, but it takes many, many pages of very hard analysis. It took us a couple of years to figure out how to do. But the takeaway message is the following. You have a true solution you're trying to approximate. And because this is a finite element method with a built-in iteration, you can't just track the mesh size. You have to actually track the iterate as well. So it's U star, the solution, minus UKH. And it turns out the error at a given iterate and a given mesh decomposes into 2 terms. The first term depends only on alpha, and the second term depends only on H. And that's really important. First of all, the first term actually only depends on the sum of all the alphas. So we need this first term to go to 0, which happens as long as the sum diverges, which could happen if you fix alpha to be constant. Alpha could even decay, and you could find a sum that diverges. So that's nice, no singular parameters. But if you want the left-hand side to be less than a tolerance, it's enough to make the right-hand side less than a tolerance. And you can see that if you keep making more iterations, once you're less than a tolerance, you will stay less than the tolerance. Or if you keep defining your mesh, you'll stay less than the tolerance you were originally at. This doesn't happen in a lot of other algorithms, because alpha and H, or whatever substitute for alpha you have, depends on H, which is mesh dependence. This means the proximal Galerkin is mesh independent. It's a mesh independent number of iterations asymptotically to get to a fixed tolerance. And I mentioned very briefly the main competitor for the obstacle problem was the interior point method, if you actually just count number of iterations. But you can apply this method to problems that actually aren't optimization problems, it turns out. So, in fact, general variational inequalities, or your bilinear form isn't symmetric. There's many applications, fluid mechanics and financial mathematics. And the way you do it is you just substitute where the J prime was, the derivative of your ejective function, with the monotone operator A. Otherwise, the algorithm exactly the same, discretizations are exactly the same, and you just iterate. In this case, what we can prove is a little bit more limited because we don't have an energy dissipation property, because there's no necessary concept of energy when you're in this non-symmetric metric setting. But you can approximate the ergodic mean of all of your iterates. That's what U bar is. And you get the same type of error estimate decomposing into the optimization error and the discretization error. And now, in the last couple of minutes, I'm going to go over a few other example problems. Contact mechanics and obstacle problems, you always have the same type of constraint. Unilateral bound constraints, you always use the same type of Legendre functions. You always have an exponential here. If your feasible set has upper and lower bound constraints, this appears in topology optimization or variational fracture. You could use the Fermi-Dirac binary entropy, and the main difference is that your nonlinearity would look something like this. Otherwise, the scheme is about the same. If you have gradient constraints, you can use the Hellinger entropy. So the first example I showed you was the iconal equation, but there's also plasticity models where instead of minimizing this objective function, you minimize, for instance, the Dirichlet energy is the most basic example. In multi-phase flows, the constraint is multiple material densities or phase densities. They all must sum to 1 at every point. We've used this for multi-phase Cahn-Hilliard equations, as well as multi-material topology optimization. There are problems largely in liquid crystals and Monge-Ampere equations where you have constraints on the eigenvalues. So in Monge-Ampere, you want the solution to be convex. It's convex, you have a unique solution. It's very, very, very difficult to design a numerical scheme that guarantees, as a high order at least, that guarantees you a convex function. But there's a Legendre function, it turns out, for this space of positive semi-definite symmetric matrices, which can be leveraged here to give you a high order, actually exponentially convergent scheme for Monge-Ampere. And in liquid crystal constraints, you sometimes have upper and lower bound constraints on eigenvalues, and then you have to generalize the Fermi-Dirac entropy to matrix valued variables. The last thing, and I'll just be a few minutes on this, we've recently, this was work Doyen Kim did, started a project in multi-material topology optimization, where we needed to find a Legendre function for an arbitrary convex polytope, and we couldn't find one in the literature. Well, Doyen found one. We're very excited about it. Basically, you take all the vertices of your convex polytope, you put them into a matrix, and you substitute that matrix into this formula, and you have the one direction is very hard. Unfortunately, it's not the direction you have to ever use. We always look at the gradient of R star, which is this beautiful, smooth, infinitely differentiable formula here. And this allows you to navigate any convex polytope. And we started using this. So this is joint work with Boyan, Peter Gangel, and Thomas Surowitz. Electric motor design, where in the stator, you need to choose direct polarizations of your different magnets. So you can change those polarizations at different points. This is what an optimized magnet distribution would look like. Touching your stator here in this coil, or in structural design, where you might want to place different materials with different anisotropies in their stiffness, and for a standard type of cantilever beam problem, but now with the multi-angle or anisotropic topology optimization, you get an optimal design that looks something like this. We're also studying the PDEs. I won't say too much about this, that arise actually at the continuous PDE level, because you can prove very interesting things about the pre-discretized algorithm. And we've also started applying this to multi-body contact with a feasible set, depends implicitly on the solution U. Now, just to wrap up here, in summary, Proximal Galerkin is a unified framework we're building out here at Brown and in other places to tackle variational problems with inequality constraints. I gave you a brief overview of theoretical aspects of the algorithm, but if you're interested, I can send you a lot of papers that go in much more detail into the theory. And if you like what you saw here, please follow this QR code. Reach out to me and I can send you the slides. I'm more than happy to do that. Or reach out to me, tell me about a problem that you're working on with inequality constraints. I'd love to hear about it and potentially add you to this list of fine characters here. Thank you very much.
Thank you, Brendan. That was very impressive. Very nice talk.
Let me add
Yeah.
this thing you see on this last slide. We'll have a paper out on this soon. This is manifold constraint. Maybe next time.
I have one small question for now. I know you showed mesh independence. You're solving the sequence of the nonlinear problems, and that iteration count is mesh independent. How about the nonlinear solver within?
So the proof is elusive. We have some ideas, but if you do things right, and we actually saw this right away, and even in the first paper, we have a table, but it's not in the slides.
Mhm.
Usually what you see is that in the first outer loop, you need,
Mhm.
I don't know, a handful of Newton iterations to find your solution. And then you use your previous solution as you inform your initial guess for the next Newton algorithm. And you will see fewer iterations
Fewer.
required to get your
Mhm.
next subproblem solution. Until
Okay.
actually, usually what I see in my own experiments is that after 3 or 4 outer loop iterations, you just need one Newton solve. And that's it. So it just
Getting
becomes
closer actually helps you.
that's right. It's so that they're basically the final stages of this algorithm, or the majority. I mean, we're talking about everything after the fourth or fifth outer loop is just one linear solve, and then you go back and you do the next outer loop iteration. So this is what we observed, and you can tell. I mean, if it's just one solve per inner loop, then it's mesh independent too. But proving this is difficult because the theory of mesh independence for Newton is a bit brittle, and we may need to expand it in order to actually apply it to this class of problems.
Sure. First, thanks for the great talk, Brennan. I mean, really nice to follow here, also for a non-mathematician. I have 2 questions on the Eichner part. I mean, the first one would be on the efficiency. Is there any advantage of using the proximal Galerkin methods to the specialized solvers which we already have, like fast iterative methods or fast marching methods?
Well, it's sort of case by case. I think this current solver we have, FEM example 40, could use some further development. Because to make it absolutely efficient, you need a precondition. You need to think about the entire solver pipeline. This is a PhD student project that we're hoping to start later this year, because we just got some funding to look at it. But right off the bat, before you consider those aspects, there's an appeal to using a finite element method to solve these problems, because often you want to solve them at some point in a finite element workflow. and you don't want to break that workflow, go to a fast marching scheme or some much lower order scheme. You want to do the solve right inside the code you're using to do everything else. So that's what I see as being the primary advantage at this point. But I should also say that it can solve this problem pretty fast. We haven't done a head-to-head comparison with fast marching though.
Okay, thanks.
Yeah.
Kind of makes sense that, I mean, preconditioners is always a difficult topic to find them for specialized problems. And my second question here would be, what about the anisotropic version of the Eichner equation? Have you also looked at this already?
We have not looked at that. No, that's complete open territory.
Okay, thanks.
Yeah.
Great talk, great talk. Very exciting stuff. I was curious, this is maybe more of a clarification question, but the utility approximation that comes out of this that we say that is like globally bounds preserving, do you only get that when your B operator is the identity? I can't
That's
imagine.
right.
Okay. And then
Yeah.
so doing something like high order Signorini problem, you wouldn't necessarily have a like globally bounds preserving solution because it's the trace operator. I see.
That's right. I mean, you get something that's preserving the bound, but is it physically relevant? Maybe case by case basis. I'm not sure. Yeah.
I see.
We're not quite sure what to do with the Signorini
Yeah.
variable right now.
I think I also have a kind of a follow-up question.
Yeah.
The comparison I saw, I haven't seen the examples that you showed towards the end with the mesh to mesh contact. But I don't know, how does this formulation compare to like mortar methods?
Oh, it's compatible. We don't care how you discretize.
Okay.
So we're actually in the process of implementing this with tribal, the tribal interface.
Okay.
We just don't have the results yet.
Very cool. Very exciting. Thanks.
Yeah, I should let me add to this. You don't even need to use there's no reason to use conforming subspaces. We have a new paper with Beatrice Riviere and Alexander Aaron where we look at discontinuous Galerkin approximations. Pretty much all the results I showed you here go through with some minor modifications. Same would probably hold with mortar methods.
I guess I also maybe have another follow-up.
Yeah.
Has anyone done any sort of like computation of like discrete adjoints with like something like pi adjoint, like with this like framework at all?
This guy might have.
Okay.
I should actually update his figure. He's not at the Weierstrass Institute anymore. He's now at Oxford. But I think John or Patrick Farrell would be
Very cool.
or people to reach out to. They would be very excited to probably follow up with you if you reach out to them.
Cool. Thank you.
Oh, I see. Can the constraints become tight in one of the iterates, or is there always a slack in the inequality constraints? I can there's two interpretations of this question. So Paul, either clarify in the comments or just
Yes, I'm
unmute
here.
yourself. Okay. Do you mean does the iterate eventually enforce the constraint, like reach the boundary of the feasible set, or do you mean that can the feasible set kind of squish to like become singular with zero
That
interior
reaches,
at a point?
yes, that it reaches the boundary so that the
That it
inequality
reaches the
becomes an
boundary.
actual equality.
So theoretically no, but practically yes. Because let's just go to the obstacle problem case. Here, so the exponential goes to 0 very, very fast. So once psi is -40, exponential of -40 is less than machine epsilon. So you're within machine precision of the obstacle, which for all intents and purposes is touching the obstacle, numerically speaking. Is that satisfying?
Yes, thank you very much. Yeah.
Okay, yeah.
Okay, thank you, Vernon, for this very nice presentation. I was more interested in the fracture model. You have presented at some point of the slides a list of, let's say, the transformations to be done. Yeah, a list of transformations to be done. Okay, anyways, here, let's say this in the fraction model, the primary unknown is the damage, and which has to be between phi1 and phi2 for you. So it's not. So typically what we have in damage models is the damage should always keep growing. So
That's right.
phi1, phi2, I imagine are the limits for damage before and after. But normally we don't have this phi2, let's say the higher value, because it's a continuous, time continuous constraint that we are looking at.
Well, so let me clarify. In fracture, phi2 would be 1 because it's a density variable. It's supposed to go between 0 and 1. Now, you can choose not to enforce that constraint if you don't want to. It's the lower bound that's most important. I agree with you. And then that would depend on the previous solution. So as there'd be yet another outer loop where you would increment time or pseudo time. And just keep pushing up that lower bound.
Okay,
until
so this
it
is the
gets
upper
pretty
and
close to
and
1.
lower bounds. So these are the physical upper and lower bounds. But normally also we have another constraint where all this row has to keep growing as well. So there are two constraints to satisfy. It has to be between 0
Of course.
and 1. So
Of course,
case,
and in that case, phi1 is the previous value of rho.
Okay. And I think I get it, but typically there are two constraints. One is that this row has to be between 0 to 1, but also row has to keep on increasing. This feasible set would be either one of those, right?
It ends up, if you look at the intersection of the two sets, and the intersection can be described as this, like this, where phi1 is the previous value of rho, like rho k minus 1, and phi2 is just 1.
Okay.
This is all explained in a paper that appeared on arXiv last week. Unfortunately, it's not the one in this QR code sends you to the topology optimization paper. But if you search for Kara, Basilev's, Surowitz, and me, you'll find the fracture paper where it's explained in further detail.
I'll take a thanks.
Yeah.
Michael Tupac.
I was just curious, it's kind of like a practical thing, but you have sort of this latent space variable psi, and you have the regular variable u, whatever physics, and right, because you're in the latent space, sort of the dimension or the scaling are quite different. So I was just kind of curious how you guys can think about like the tolerancing, right? Because you're going to solve this thing to a certain tolerance, and you have like the first equation to a certain tolerance, and the second equation to a certain tolerance, and like how do you think about that? I mean, it's a problem with all methods, but just kind of curious.
Michael, a great question. So you don't want to look at the residual of the latent variable. You actually want to, bear with me, you want to look at a derived quantity in terms of the latent variable, where what you do is you take the first equation, you divide through by alpha, and you can move this right-hand side back over to the left. So B star of the divided difference of the latent variable actually approximates your Lagrange multiplier. And you want to look at the residual of the Lagrange multiplier part of the equation and UK. And in that case, you can develop stopping criteria that look very much like stopping criteria for other methods. You don't have to worry about the scale. The Lagrange multiplier has standard units, and so does the primal variable. So you can pull most successful stopping criteria off the shelf. But looking directly at the latent variable is not the best way to go.
Nice. Makes sense. I have a second question. So like, let's say you have like a non-convex, bound constrained minimization problem. I do problems with buckling and stuff, and fracture does this too sometimes, right? Depending on the regime. And so then you don't have a positive definite sort of upper left matrix and stuff. And so I don't know, have you guys sort of embraced all that or dealt with that?
We have some of it blindly, because first I don't want to prove something about a method that's not going to work, so I'm going to implement it first and test it out. And we've seen some early successes in a few non-convex problems, and we're slowly sort of building out the theory. So for fracture in particular, you're biconvex. You're convex in U and you're convex in the damage variable independently, but not together. So you can split it, as people often do, and you get two convex problems. Or you can actually solve the whole monolithic scheme, or the monolithic system of equations, and that's what we did in our first paper. Both approaches seem to work, but as you might expect, the monolithic approach needs a good initial guess. It's a little more brittle.
Yeah. There are certain regimes where the positive definiteness will probably be painful, but for steady crack growth, it's probably totally fine. All right. I just want to say one thing, because we were talking about the iconal thing and the finite element. Just be aware of, there's this heat method by Crane. So it also solves in a finite element math. It's sort of a graphics technique, so it's kind of like less accurate, but just so you're aware that it exists.
I'm aware of this. This is again, so there's a parameter continuation that has to happen here. There's actually a few others. There's one where you look at the p goes to infinity limit of a p Laplacian, and there's this heat method where you take like prime to 0. They all have these like singular parameters and these drawbacks that come from it. So I think ours is pretty competitive versus those, but I think I see what you're saying. I mean, there are other ways to solve iconal with finite elements.
I'm not trying to say it's like the way one should do it. I'm just just so you're aware that it exists,
Yes.
but you do, so it's fine. Yeah. It'd be cool to have a more rigorous thing, because we use this for some things and we find like it kind of has some spurious oscillations and stuff that are undesirable. So we'd actually like to try something a little more rigorous at some point. So
Let me know. There's FEM example 40. I'm not saying it's perfect, but it's there. And we'll probably be adding to it soon over the next year.
Nice. Yeah, thanks.
Yeah.
So first, really impressive talk, Brandon, and in general, this whole research program you've established, very impressive. Can you comment on the preconditioning of the linear systems?
It depends significantly on the choice of discretization. So the cop-out question is to say that if you use a hybridizable discretization, then by some hybridization magic, it's explained in 2 papers, but most clearly in the most recent one with Beatrice and Alexander. Each subproblem is positive definite once you statically condense. So anything you want off the shelf could be used there. If you do not use such discretization, then, and this is entirely experimental evidence as far as I know, the BDDC preconditioner seems to do really well. Now I don't know if that can be made matrix free or that's going to be super scalable, but it's right there in PETSI. You can plug into it. It seems to do pretty well for this class of problems. And then if you have specialized domains and elements, John Papadopoulos, this clever guy right here, has a paper specifically that specifically tackles high HP and preconditioning, but it's used some ideas from spectral methods and really exploits the structure of the domain. But it's another preconditioning direction one can go into.
Is that specifically for contact?
He did contact. He did. I think he did obstacle, not real contact there. And he did this elastoplastic torsion problem, which is this constraint with this objective function. But no, it's not for contact. Actually, I think the preconditioning with normal contact with Signorini probably be easier than some of these other classes of problems. But yeah, it's definitely ongoing research. So maybe ask me again in 6 months to a year and I'll have a better answer for you.
All right. Thank you.
Yeah.
Very nice.